Hello, geometry students. Here is what you would miss if you were absent from Zoom class on day 3 of geometry. So you won't be able to do the Zoom poll. You won't be able to do the Google Slides activity, and you won't be able to do the exit ticket, but you can follow along with this review of radicals. And we are going today talk about how to simplify a radical. And that means to write something in what's called standard radical form. Okay, so first we're just going to look at this list of numbers. It's a very special list of numbers. So the question is, can you tell what's special about these numbers? All right, I'm going to skip over 1, but if I were going to break 4 down into what multiplies to make 4, right, I could break it down into 2 times 2, or another way to look at it is 2 squared. 9 breaks down into 3 times 3, or 3 squared, etc. 16 has other options, but it also has a number times itself, 4 times 4 squared. All right, and so you see the pattern. All right, so all of these numbers are called perfect squares. 1 is always the forgotten perfect square, but it really is a perfect square. So a visual of perfect squares could be that we could actually make a square. And we could look at the sides of the square. Say this side was 6, so we would know this side would also have to be 6. And if we wanted to find the area of the square, to find an area, we do base times height, or length times width, or in a square, since they're both the same, we often use that little special formula called side squared. So take the 2 sides, multiply them by each other, you always get a squared number. Okay. When you look at just the root of these numbers, we're just looking for one of those little pairs of numbers. So the square root of 1 would be 1, right? The root number for 4 would be 2. The root number to 9 would be 3, etc. 4, 5, 6. All right, so a lot of times in math, you are asked to find the square root of something. And so to find a square root, we would never write it out with the words square root. We would use the special square root symbol, which looks like this. All right, also called a radical symbol. Radical. Okay, so these examples down here, the square root of 100 is just us, answering that question, what's the root number for 100? What's that number that when you times it by itself, you get 100? And so that number would be 10. And you can just write 10. I mean, a work step could be like this. You don't have to show a work step on the little ones because they're pretty easy. But if you wanted to, you could break 64 into 8 times 8, and anytime you have a pair of numbers like that under a radical sign, you know you have a perfect square. So the root is just one of those numbers, 8. It's also true, you could kind of write this as a work step. 121 would be written as the square root of 11 squared. So that's just 11. All right, so what you had to learn in Algebra 1 was this concept of standard radical form, aka otherwise known as simplest radical form. So if you see the directions for standard or simplest, then they're asking you to do the same thing. Okay, so when you simplify these square roots, we want to have the idea that we're not going to grab a calculator and give a decimal answer. And we're not going to leave any perfect squares under a radical. So we couldn't leave an answer like this, square root of 25, because 25 is a perfect square. Right? So we'd have to simplify it to its root number. And number 3, we want to have no factors that are perfect squares under a radical. And that's kind of where our more complicated review begins. Okay, so when you think about the square root of 13, what we know is 13 really doesn't have any factors other than 13 and 1. It's prime. And 13 is a perfect, I mean, 13 is not a perfect square. So there is nothing to do with this problem right here. 6 is not a perfect square. One thing that people try to do is to say, oh, I could break 6 down into 2 times 3, but these are factors of 6. 2 is not a perfect square, and 3 is not a perfect square. So we're not going to actually do that step right there. Even though we can break it down, we keep it as square root of 6. 20 is a little different, though. It has some factors, and so we're looking for some factors, a factor that would be a perfect square. So I'm just going to kind of write them down, right? You know, there's 1 and 20, which doesn't help us at all. 2 and 10, that's another pair of factors that multiplies to make 20. And 4 and 5. So we have, oops, I hit something. Sorry. 4 and 5. Okay. So we're looking at our factors right here. And we notice that that is a perfect square. So what we are going to do is, erase that little thing right there. And we're just going to do a breakdown for our first step. I'm going to purposely write it this order to show you that it doesn't really matter if you put the 5 first or the 4 first, but in your final answer, it kind of does matter how you write your final answer. So all I did was a breakdown. 5 times 4, but I didn't do any square roots, so I have to keep them both under the square root symbol. You can't do anything with the square root of 5, but the square root of 4 is a perfect square. So you could write it as 2. And this is an awkward way to leave your answer. So the number that's outside the radical goes in the front, and the square root number goes second, and you will usually never see the multiplication dot, but you got to know what it means. When you see it written like this, it means to do 2 times the square root of 5. Okay. Next examples. What do we do when we get really big numbers like the square root of 325 and 396? Okay. So I'm a big fan of the factor tree. So I'm going to write 325. I should have left a little more space here. So I'm going to write 325 here, and I'm going to just break 325 down into some factors until I get it down into some workable numbers. So a couple tricks, like, first of all, most people, when they see a 5 at the end, think that the number is divisible by 5, and that is right. So you could just divide 325 by 5 and get 5 times 65. All right, another number that ends in a 5. So 5 times 13. Okay, and now I'm going to use my tree ends. And I'm just going to write a little statement down below. All the tree ends, you got to use them all. They always multiply back together to make the number the big number. This together is going to make a perfect square. So together, 5 and 5, if you multiply them back, is 25, right? Times 13. So square root of 325, I did the factor tree to help me break it down into square root of 25 times square root of 13. All right. Square root of 25 is a regular 5. Square root of 13 is just square root of 13. And you typically will never see the dot there. You just have to know that when you see these two numbers side by side like this, they really do mean 5 times the square root of 13. All right. So let's do another one. 396. Maybe I'll change pen color so they don't all blob together. Okay, so first step is to just go off to the side and do a quick factor tree. So I don't know. I mean, it's kind of a big number. I would maybe, and it's even, so I would maybe just start with 2. Take 396 divided by 2. So that's 2 times 198. Take 198 and divide it by 2 again, and you get 2 times 99. All right, and take 99 and divide it by 9, and you get 9 times 11. Okay, so I'm going to stop right there. That's a tree end. We got to use all the tree ends. This is a special tree end. Even though it breaks down more, I'm not going to break it down because it's already a perfect square. So we don't want to break, we don't want to break our perfect squares down. So I'm going to down at below here, do 2 times 2 times 9 times 11. Those two go back together to make a perfect square. So now I've got 2 perfect squares. So I'm going to use those for my breakdown. You could see if you put those perfect squares together, you'd get another one, right? You'd get 36, but I'm just going to keep them separated. So 4, 9, 11. Oh, it's getting too squished together. Okay, so square root of 4 is 2 times, right? Because everything is multiplication here. Square root of 9 is 3 times square root of 11. So those dots are super helpful when you to put them in your work steps so you know what you're supposed to do. People get confused all the time about whether they're supposed to add those numbers or multiply them. And it's with this procedure, it's always multiplication. So now 2 times 3 is square root of 6 times square root of 11. I'm going to have to do the square root of 112 on a new screen. All right. Square root of 112. It seems quite a bit smaller. So sometimes I use this trick, 112, and that is a divisibility rule. So the divisibility rule is if the last 2 numbers of your number are divisible by 4, then the entire number is divisible by 4. So when I look at these last 2 numbers, there's a 12 there. Since that's divisible by 4, the entire number is divisible by 4. So I'll take 112 divided by 4, 28, and that's also divisible by 4. Oops, 4 times 7. Okay, so I got to use the tree ends, 4 and 4 and 7. So I just usually write a little statement down here. 4 and 4, I'm gonna put these back together to make an even bigger perfect square. So the factor tree is going to help me do the breakdown. And this is just so much better than trying to hunt and peck on your calculator and figure out what the perfect square is that's divisible by, that goes into 112. In this case, we found out pretty quick it was 16. Okay, so remember the breakdown step only takes your number and breaks it into factors. We didn't take any square roots. Now we do the breakdown of the square roots. Oops, I just don't do 2. 4 is a perfect square, oops, but it's not under a square root anymore, so it stays 4. Okay, so at this point, excuse me, you'd have to go back into Canvas. There's a worksheet that you would need to print off and work those problems and follow the instructions for submitting it to me. And hopefully that was enough review that gives you some place to start. Okay, thanks. Bye.